Hello everyone. Today I will introduce a new artificial intelligence using a genetic algorithm to localize the CO2 on 3D seismic data from the Sleipner storage project. After a brief introduction, I will explain how the algorithm works and then discuss its application to Sleipner by first comparing the results with the literature and second giving some additional insights on how this AI could help build better and more accurate reservoir models. So for any project dealing with the subsurface, the key to success is understanding the geology. And with the wealth of data available, then the AI can be seen as an enabler to build better and more accurate models. The thing is, today a lot of approaches are supervised, which means that you need initial training to get to the results you want. And so you introduce a bias. On the contrary, today our focus will be on an unsupervised and fully automated application of AI that can deliver very fast, independent, and unbiased examination of any kind of 3D volume or library. How it works: so the 3D volume is automatically segmented and organized into waveforms, which are equivalent to genes, if you like. These waveforms start to join together into populations called geopopulations here, based on their genetic and spatial compatibility. Each population of waveforms has a common waveform, which we call the genotype, that continually evolves as new trace waveforms are added to the population, and the evolution continues until a minimum fitness threshold is reached, and all the horizons are extracted from the volume. So for each population, you can display three attributes: amplitude, Z-maps, isochrones for example, and fitness. And fitness is something unique to Seisnetics. The fitness maps the morphology of the seismic waveform in response to changing reflector geometries. So what you see in the picture, for instance, is a geopopulation extracted from another dataset. And so the range of colors from green to blue and red tells how similar the waveform encountered along the section is to the genotype. So green, they are very similar to the genotype, and red, they are very different from the genotype. And so combining this information with well data, and you get a new level of geological details that can really help build more accurate models. So now let's quickly see the projects. Here we're talking about the Sleipner CO2 storage project, which started in '96 and for which 4D has been used successfully to track the plume. So you have 9 vintages available and different processing and reprocessings. And the thing is, looking backwards, some assumptions and uncertainties have been highlighted in the literature, which made the original predictions difficult. So as you see in the seismic baseline from 1994 on the top of the picture, then it was difficult to find surfaces and horizons to build a complete model and even to have an accurate velocity model for seismic inversion. And also another uncertainty lied into the localization and prediction of the CO2 and its migration path over the years. So the idea here is, how can we bring new perspective to this project? So we used 3 vintages and reprocessings. So it's very easy. You download the data, you load the data, and then you launch the process. And for every vintage, it took approximately 3 minutes. For 6 vintages, between 15 and 18 minutes, to extract all the geopopulations and horizons, which you can see on the example on the right side of the slide. Then you can just basically pick any horizon, look at the attributes, and even compare all the vintages and processings to make quantitative analysis and run statistics to see how it changed over time or with the processing. So just a quick example, we wanted to see if we could localize the CO2. So you have the example of the uppermost layer L9 in the literature of the Utsura formation. So on the left side, you have the fitness map, and you already see a shape in the center with similar waveforms close to the genotype. And when you change and you look at amplitude, basically what you see is a contour of CO2 in this layer, which matches perfectly the one described in the literature. So we prove here that we can get the same results, just a bit much faster. So I wanted to discuss additional insights brought by the AI, and the thing is, it's possible to compare all seismic volumes using the same unbiased approach and to run statistics to see how the number and size of populations change with processing or the presence of gas. So here, for example, I plotted the number of waveforms in the geopopulation versus a two-way time for the 94 baseline and processing of 201. You see it has extracted 827 geopopulations. And with the same for the next reprocessing of 07, you see you have a shift to the left and with less populations extracted and also smaller. Then the 2008 processing, you have a bit more geopopulations, and the same for the 2010. So you see that this tool can be used as a QC to compare the processing. Then why this is observed precisely here, that's a question that should be asked to the experts. But here what we can say is that you can make quantitative comparisons and ultimately really enhance the velocity and reservoir model. So conversely, it's been possible to compare different vintages like the 94 in 2010 to see the differences in geopopulations. So in the literature, it is mentioned that more horizons should be eliminated by the CO2 or are eliminated by the CO2 over the years, horizons that were not seen on the 94 baseline. And here we just compared the 94 baseline and two reprocessing from the 2010 vintage in 2010 and 2011. And you see that the number of geopopulations already greatly differs from the 2010 vintages, with more than 1,000 geopopulation for the 2011 processing versus 800 for the 2010. And focusing on the zone of interest where the CO2 is moving, you should see more geopopulations. And you see a difference between the 94 baseline and the 2011 processing of 2010. But for the processing of 2010 for the same vintage, you have much less geopopulations. And that's also an interesting fact. Of course, same question, which remains open, is why, and that's could be interesting to discuss with people who have much more experience on this project. And so finally, by analyzing the fitness maps on all the sections and vintages, you can also check the continuity of horizons, compare all the attributes, and look for what we call the funny looking things, which basically are some changes, ruptures in geopopulations, understand why it's like that, see continuity of horizons, and compare this over the years. You see, for example, the CO2 eliminates populations. You have horizons that appear here that were not seen on the baseline. You also see the velocity change, the impact of the CO2 on the seismic wave velocities, where you see less populations here than they were on the baseline, and the same for the 2010 vintage. So you can really compare all the vintages and see the differences in terms of attributes and also in terms of geopopulation size and localization. So in conclusions, this AI has been used successfully to replicate results on CO2 localizations. It's been helpful to check the different reprocessings, but very interestingly, also you can look for migration paths eventually and see where the CO2 can move when you look at the baselines. You can really better understand the subsurface. And finally, it would be very interesting to process all the 48 volumes and compare all the geopopulations, run statistics, and even compare the attributes. So with this, I'd like to thank my co-authors, Equinor and Sintef, for the release of this data online, and I would be happy to answer any question if there were.